Okay, so today we're going to move on to something called hypothesis testing. Well, a hypothesis is a prediction or an idea about something, and we're going to test these hypotheses based on data that was collected in a sample and judge the likelihood of this sample being the case based on what's called a significance level. These are much easier to explain when we're in context. So although I've briefly mentioned them now, I will add more information as we go. Quite often we use what's called the 5% significance level. And the reason that comes up quite a lot is because in psychology and in other disciplines where we might be comparing or testing a hypothesis, 5% is deemed the level we go on. So basically, if something has a lower probability of 5%, it means it's such a low probability of actually occurring that there must be some kind of change, some kind of difference compared to what we thought was the case. So that's why we quite often use it. So the first thing we need to do to set up a hypothesis test is we need a null hypothesis, which we often call H0. And this is our original idea that we assume to be true. We then have our alternate or alternative hypothesis, which we call H1, which is our new hypothesis that we are testing. Now, we are particularly looking at hypothesis testing with binomial, and we are testing the probability. So we think that the likelihood of something is P, and we are testing to whether that P is likely to be true or not. So the first thing we're going to do is we're just going to practice setting up our hypotheses. So on the second slide, so John wants to see whether a coin is unbiased or whether it is biased towards coming down heads. He tosses the coin 8 times and counts the number of times X that it lands heads uppermost. So it says describe the test statistic. So our test statistic is going to be that it is a binomial distribution where X is binomially distributed with a sample size of 8 and a probability of a half, where P is the probability of landing heads upwards or uppermost. So that's our test statistic. Write down a suitable null hypothesis. Well, the null hypothesis is that the probability of landing on heads is a half. So it really does need to just be as simple as that. Our alternate hypothesis, well, he thinks that it's biased towards heads coming uppermost. So he thinks the probability is larger than a half. So that is what our null and our alternate hypothesis would look like in this particular example. So now we're going to look at a bit more in context how we might look at what a null and alternate hypothesis is and how we would describe the condition with which we would reject the null hypothesis. So an election candidate believes she has the support of 40% of the residents in a particular town. A researcher wants to test at the 5% significance level whether the candidate is overestimating her support. The researcher asks 20 people whether they support the candidate or not. 3 people say that they do. Write down a suitable test statistic. So again, we know that something must be binomially distributed, and in a sample of 20 people, excuse me, we are testing the likelihood that she has 40% of the support. So that's the probability of being supported so the probability of supporting the candidate is P, which she believes, or he believes, is 40%. Write down 2 suitable hypotheses. So that's H0. So the probability that we believe to be true is that P is 0.4. That's what we currently believe is true. The alternate, which is what the researcher is trying to do, is that the researcher thinks the candidate is overestimating. So that means the reality of the support is that it's less than 40%. So C, explain the condition under which the null hypothesis would be rejected. So what we want to know is how likely is it that 3 people or less would say that they support this candidate, given that we've asked 20 people who they support. So we know that there's a 40% chance of people supporting her from what she says. I've assumed as she, I apologise. Oh no, it does say she. Okay, I haven't assumed. She has a support of 40%. So she thinks 40% of people support her. Now, when you take a sample, it's not going to be that if every single time you take a sample, 40% of people will support her. The likelihood is that sometimes you'll take a sample and more than 40% will support. Sometimes you'll take a sample and less than 40% will support. But is that sort of error within an acceptable range to say, actually, no, just because, let's say we took a sample and 20% supported her, that's still okay, that's still within a given range to say the likelihood is that she is still right. So what we're doing is we're comparing the likelihood that less than or equal to 3 people say they support her. So we are comparing this probability with a 5% probability. So what we're saying is that if the probability that that 3 or less people support her, if this is bigger than a 5% chance of occurring, sorry, just move my pencil case out of the way so I can move my paper. If we think that 3 people or less has more than 5% chance of happening, then we do what's called accept our null hypothesis. And what that means is that this probably is still likely enough to happen that our original idea that 40% of people support her must still be true, because this still has a really good chance of happening. It has more than 5% chance of happening, so our original premise must be true. But if the probability that 3 or less people is less than 5%, so if it's less than 5% likely that 3 or less people out of 20 would support her, then we would reject the null hypothesis, because it's so unlikely that 3 or less people in a sample would support her, given that 40% of people should. That's so unlikely to happen that our original premise must be wrong. It can't be that 40% of people support her, because this is so unlikely to happen in a sample that we must be wrong. And if we reject the null, we then accept the alternate, which is that less than 40% of people must support her. Because it's so unlikely to happen if 40% of people support her, that it must be that less people support her. Okay? So it's on these conditions. So I'm going to show you to start with in the context of a one-tailed test. So moving on to one-tailed tests. Now, if you're watching this video, you'll probably have noticed, if you're trying to follow alongside the book, that I have done it quite differently to the book. That's because chapters 7A and 7B, or 7.1, 7.2, they try and do a lot of things out of context, and it's actually really difficult to understand hypothesis testing outside of context. So I've basically gone straight to the one-tailed test section, having just sort of summarised things for you. I'm going to do 2 different types of examples. Then I'm going to give you an exercise to work on, and then I'll give you a video on two-tailed testing. So a one-tailed test, this is where we believe that the probability is specifically bigger or smaller than the null. So we actually have a given direction for our probability. So I'm on what I think is the, let me check, 1, 2, 3, 4. I'm now on the 5th slide, and I'm going to do that example. So the standard treatment for a particular disease has a 2/5 probability of success. A certain doctor has undertaken research in this area and has produced a new drug which has been successful with 11 out of 20 patients. The doctor claims the new drug represents an improvement on the standard treatment. Test at the 5% significance level the claim made by the doctor. Okay, so the first thing that we need to do whenever we do a hypothesis test is set up our hypotheses and our test statistic. Statistic. So our test statistic is that our variable x is binomially distributed, and we're looking at a sample size of 20 patients, and at the moment we believe the probability of success is 2/5. So our null hypothesis is that the probability is equal to 2/5. Our alternate hypothesis is we think that this drug is more successful now. We think there's been an improvement. So the probability of success in curing patients is greater than 2/5. So our next step is calculate the probability of the occurrence of our sample. So this means we are looking at what happened in our sample and testing the likelihood of that happening given our initial assumption, which is that probability is equal to 2/5. So I know that 11 people in our sample were successfully treated. So I need to work out the likelihood that 11 or more people could be treated, assuming our probability is 2/5. Now, I'm looking at 11 or more because we think there's been an improvement. So that means we need to have a look at 11 or larger, because 2/5 of people, well, 11 or less means that we could have around 2/5 looked at, which is obviously likely to happen. So we need to look at the likelihood of 11 or more. We're looking at an improvement, which means that we are expecting, or we need to compare a larger than section. So the probability that x is larger than or equal to 11 we need to see what the probability of that is. Now remember, my calculator can only do the probability of less than or equal to. So if I'm looking at the probability of 11 or more, that's 1 take away the probability of 10 or less, which is what my calculator can do. So, menu, I need to go to distribution. Now I'm looking at binomial CD. Now I want the variable because I know what I'm looking for. So 10 or less in a sample size of 20, where the probability of success is 2/5 or 0.4. So the probability of getting 10 or less is 0.872, and I'm just going to do a couple more significant figures. So the probability of 11 or more is 1 minus that answer. So 1 minus 0.87248, which is 0.128 to 3 significant figures. So we've worked out the probability of getting a sample size of 11 or more, assuming that our probability is 2/5. So our final step is to compare our probability with the significance and conclude our hypothesis. Well, 5% I have to write as a decimal, which is 0.05. And I'm just going to move that up so you can still see our hypotheses rather than my first steps. So 0.128 is larger than 0.05. So the likelihood of getting 11 or more has around a 12.8% chance of happening. This is greater than 5%. So therefore, we accept our null hypothesis, because this is still, assuming our probability is 2/5, the likelihood of getting 11 or more people is greater than our cutoff. So that means it's likely enough to happen that my original problem is probably still true. So I'm going to accept the null hypothesis. The doctor does not have the evidence to show an improvement. So in reality, what you'd think is that actually just this sample, they were particularly lucky. So these people just happened to be particularly successful. It means in another sample, probably there'd be quite a small rate of success, but they are both acceptable within the range given 2/5 of a probability. So that is our conclusion. So we're going to look at another example of one-tailed tests. But this time, we're going to be looking at finding what's called the critical region. Because these are the two types of questions you'll get for one-tailed and two-tailed. So on the next slide, I've taken this from the exercise because, again, given that hypothesis testing is quite a difficult topic, it doesn't really do many examples, or it doesn't do a variety of examples. So I'm going to one where you're finding the critical region, because they're both two different types of examples you'll get. So a plant germination method is successful on average 4 times out of every 10. A horticulturist develops a new technique which she believes will improve the number of plants that successfully germinate. She takes a random sample of 20 seeds and attempts to germinate them. Using a 5% level of significance, find the critical region for a test to check her belief. Okay, so the first thing we need to do is exactly the same. We need to set up our test statistic and our hypotheses. So we're going to say our variable is binomially distributed in a sample size of 20 with a probability of 4 out of 10, which is 0.4. I know both examples I've chosen have the same sample size and same probability. The reason that a lot of the probabilities and sample sizes will be quite similar is because they're generally encouraging you to use the table, even though I won't be. So don't worry about that. It's not. That's why it's not as varied as you might imagine. So our null hypothesis is that the probability is a 4 out of 10 germination. And the alternate, well, they think that this new technique will improve it, so more than 40% or more than 4 out of 10 will germinate. So now we need to find our critical region. So we are looking for there to be an improvement. So we are testing at the 5%. So what we need to find is the probability of getting more than or equal to a particular value is less than 5%. Now remember our calculator. This is where we need to use our calculator to work out our critical region. Now we're going to use the list function. So I want to know the value where x is greater than or equal to a number is less than 5%, which means I need to use my calculator to find when x is less than or equal to a particular value is more than 95% chance, because that means that being greater than the next value up will have less than a 5% chance of happening, and this gives us our critical region. Now it's quite useful to do this on a bar model. So here is my 0 to 100%. And because I'm looking for improvement, I'm looking for something at the 95% cutoff, because then it will have, or be in this region of the less than 5% chance of happening. So what I'm going to do is I'm going to go on my calculator again. I'm going to go to distribution, go down to normal CD, but this time I'm going to go to list. So I've got a sample size of 20, and I want to know when it's greater than a particular value, I've got a 95% chance. So I reckon I could start from x is 10, because I reckon if I get a sample size of 10 or less with a 40% chance, it's definitely going to be within the region, so it's going to have a relatively high probability, but not so high that it's more than 95% likely to happen. So I'm going to do 10, 11, 12, and go all the way up to 20, because obviously that's my sample size. Now, you can absolutely type in every single value, and I might find when I do this that I've already gone too far, which is okay. If you see me do that, that's fine. You'll just see how I'd adapt to it. So my sample size is 20, and my probability of success is 0.4. So, the probability of getting 10 or less is 0.872. Now, I want to find, in the exam, they ideally want you to show the ones either side of your cutoff, basically because it shows you're understanding the table and you haven't missed out a value. So 11 or less has a 0.943 chance. So that would be here. So that's 11 or more is 11 or less is 0.943. The next one down is 12 or less has a 0.979 chance of happening. So this one is the first one that is bigger than 0.95. So therefore, the probability that x is less than or equal to 12 is 0.979, which would mean the probability of having 13 or more is 1 minus that value. 1 minus 0.979, I should use more decimal place, more significant figures, but 0.021 chance. So therefore, our critical region is that x has to be more than or equal to 13. So our critical region is what's going to be the cutoff point. What's going to straight away tell me, if I get a sample with that many people in, that I reject my null hypothesis and accept my alternate. And you have to have, out of a sample of 20, 13 or more people, 13 or more plants germinating to say, yes, the new technique that the horticulturist has developed must be changing, must have changed our value. So B, the horticulturist has a sample and finds that 14 out of 20 have germinated. Comment on this observation in light of the critical region. Well, 14 is within our critical region, as 14 is greater than 13. Therefore, we can reject the null hypothesis and accept the alternate hypothesis. The new technique will germinate more than 40% of plants. So there's two examples, one of using actually working out the probability and comparing to 5%, and one of looking at finding a critical region. As you're doing the questions in the exercise 7C, please do keep going back to these videos and compare them to your examples. Obviously, you're welcome to email me or message me on Show My Homework, and I'm happy to help you through. But that's how you look at one-tailed tests. In your next lesson, I'll give you a video on how to do two-tailed tests.